Section 210.19 of the 2005 National Electrical Code addresses voltage drop. It states that the voltage drop on branch circuit shall not exceed 5% of the nominal voltage at the load. Table 210.20 provides the maximum allowable voltage drop for branch circuits. For a 120 volt circuit, the maximum allowable voltage drop is 6 volts. To determine the size of wire to run, calculate the voltage drop. The voltage drop is equal to the resistance of the wire multiplied by the current flowing through the wire. The resistance of a wire is determined by its length, cross-sectional area, and material. The cross-sectional area of a wire is measured in circular mils. The higher the circular mil area, the lower the resistance. The material of a wire also affects its resistance. Copper has a lower resistance than aluminum. To calculate the voltage drop, use the following formula: voltage drop equals the resistance of the wire multiplied by the current flowing through the wire. For example, if you are using copper wire with a circular mil area of 1000 circular mils and you are running a current of 30 watts, first you need to determine the amperage. Amperage can be found by dividing the wattage by the voltage. So 30 watts divided by 120 volts equals 0.25 amps. Now you can determine the voltage drop. The voltage drop equals 0.5 ohms per foot multiplied by 220 feet multiplied by 0.25 amps, which equals 2.75 volts. Since the voltage drop is less than the maximum allowable voltage drop of 6 volts, you can use 1000 circular mil copper wire to feed the weather station. When determining wire size for electrical circuits, it is essential to consider voltage drop to ensure that the equipment receives the proper voltage for optimal performance. Voltage drop occurs when the voltage at the load end of the circuit is less than the voltage at the source due to the resistance of the wires. Excessive voltage drop can cause equipment to malfunction, overheat, or not operate at all. The National Electrical Code provides guidelines and recommendations for minimizing voltage drop in electrical circuits. Firstly, it is crucial to calculate the total length of the circuit, including both the outgoing and return conductors. The longer the circuit, the greater the potential for voltage drop. Secondly, determine the current flowing through the circuit. This can be calculated by dividing the power in watts of the load by the voltage of the circuit. The higher the current, the greater the voltage drop. Thirdly, select the appropriate wire size based on the current and the allowable voltage drop. The National Electrical Code provides tables that list the allowable ampacities of different wire sizes. Choose a wire size that can handle the current without exceeding the allowable voltage drop. The allowable voltage drop is typically expressed as a percentage of the source voltage. For branch circuits, the National Electrical Code recommends a maximum voltage drop of 3% for lighting, heating, and power loads, or a total voltage drop of 5% for feeders and branch circuits combined. To calculate the voltage drop, use the following formula: voltage drop equals the current multiplied by the resistance of the wire. The resistance of the wire can be found in the National Electrical Code tables or calculated using the wire's circular mil area and length. The circular mil area is a measure of the wire's cross-sectional area. The larger the circular mil area, the lower the resistance. Copper and aluminum are the most common materials used for electrical wiring. Copper has a lower resistance than aluminum, so it will result in less voltage drop for the same wire size. However, aluminum is lighter and less expensive than copper. When selecting wire, consider the trade-offs between cost, weight, and voltage drop. In addition to wire size and material, other factors can affect voltage drop, such as the type of insulation, the ambient temperature, and the presence of other conductors in the same raceway. High temperatures can increase the resistance of the wire, leading to greater voltage drop. When installing electrical circuits, it is important to follow the National Electrical Code guidelines for minimizing voltage drop. This will help ensure that the equipment receives the proper voltage and operates safely and efficiently. Using the correct wire size is critical for preventing excessive voltage drop and ensuring proper operation of electrical equipment. Voltage drop refers to the decrease in voltage that occurs along a conductor due to its resistance. When the voltage at the load end of a circuit is significantly lower than the source voltage, it can cause various problems, including reduced performance, overheating, and even equipment failure. To determine the appropriate wire size for a specific application, several factors need to be considered. Firstly, the length of the circuit is a primary factor. Longer circuits will experience more voltage drop than shorter circuits with the same wire size. Secondly, the amount of current flowing through the circuit is crucial. Higher current levels will result in greater voltage drop. Thirdly, the allowable voltage drop percentage must be determined. The National Electrical Code recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. Fourthly, the type of conductor material, typically copper or aluminum, affects the resistance and, therefore, the voltage drop. Copper has lower resistance than aluminum, making it a better choice for minimizing voltage drop. The formula for calculating voltage drop is as follows: voltage drop equals current multiplied by resistance. The resistance of the conductor can be calculated using the following formula: resistance equals resistivity multiplied by length divided by area. Resistivity is a property of the conductor material, length is the length of the conductor, and area is the cross-sectional area of the conductor. The cross-sectional area of a conductor is typically expressed in circular mils. To determine the appropriate wire size, one can use the voltage drop formula and the National Electrical Code tables. The National Electrical Code tables provide information on the ampacity and resistance of various wire sizes. Ampacity is the maximum current that a conductor can carry safely without exceeding its temperature rating. The tables also provide the resistance per unit length of the conductor. By using the voltage drop formula, the National Electrical Code tables, and the factors mentioned above, the appropriate wire size can be selected to ensure that the voltage drop remains within the allowable limits. Choosing the correct wire size is essential for maintaining proper voltage levels at the load and ensuring the safe and efficient operation of electrical equipment. Failing to do so can result in performance issues, equipment damage, and potential safety hazards. Proper voltage at the weather station is crucial for its reliable operation. When the voltage supplied to the weather station is lower than its rated voltage, it can lead to several issues. Firstly, the weather station's sensors may not function correctly, resulting in inaccurate measurements of temperature, humidity, wind speed, and other environmental parameters. Secondly, the weather station's data logging and communication systems may be compromised, leading to data loss or transmission errors. Thirdly, the weather station's internal components may be subjected to undue stress, potentially shortening its lifespan. To ensure proper voltage at the weather station, it is essential to consider the voltage drop in the wiring that connects the weather station to the power source. Voltage drop occurs due to the resistance of the wires, which causes a decrease in voltage as the current flows through them. The amount of voltage drop depends on the length of the wire gauge, and the amount of current flowing through the wire. To minimize voltage drop, it is recommended to use thicker wires, which have lower resistance. Additionally, it is important to keep the wiring as short as possible. The National Electrical Code provides guidelines for voltage drop in electrical circuits. It recommends that the voltage drop in branch circuits should not exceed 3% and the voltage drop in feeders should not exceed 5%. By adhering to these guidelines, you can ensure that the weather station receives a proper voltage for its operation. If the voltage drop is excessive, you may need to increase the wire gauge or use a shorter wire run. In some cases, it may be necessary to install a voltage booster to compensate for the voltage drop. Proper voltage is essential for the weather station's reliable operation. By considering voltage drop and taking appropriate measures to minimize it, you can ensure that the weather station receives the proper voltage and provides accurate and reliable data. It is important to consider the impact of conductor material on voltage drop in electrical circuits. The conductor material plays a significant role in determining the resistance of the wire, which directly affects the amount of voltage drop that occurs. Copper and aluminum are the two most common conductor materials used in electrical wiring. Copper has a lower resistance than aluminum, meaning that it will experience less voltage drop for the same wire size and current. This is because copper has a higher conductivity, which allows electrons to flow more easily through the material. Aluminum, on the other hand, has a higher resistance, which means that it will experience more voltage drop for the same wire size and current. This is because aluminum has a lower conductivity compared to copper. When selecting a conductor material, it is important to consider the allowable voltage drop for the circuit. If the allowable voltage drop is relatively low, copper may be the preferred choice, as it will minimize the voltage drop and ensure that the equipment receives the proper voltage. However, copper is generally more expensive than aluminum, so cost may be a factor in the decision. Aluminum is often used in larger conductor sizes, where the cost savings can be significant. In these cases, it is important to select a larger wire size to compensate for the high resistance of aluminum. The National Electrical Code provides tables that list the resistance of different conductor materials and sizes. These tables can be used to calculate the voltage drop for a given circuit. When calculating voltage drop, it is important to consider the temperature of the conductor. The resistance of a conductor increases with temperature, so the voltage drop will be higher at higher temperatures. The National Electrical Code provides correction factors for temperature that can be used to adjust the resistance values in the tables. The choice of conductor material can have a significant impact on voltage drop in electrical circuits. Copper is generally preferred for applications where voltage drop is a concern, while aluminum may be used in larger conductor sizes where cost is a factor. When selecting a conductor material, it is important to consider the allowable voltage drop, the cost of the material, and the temperature of the conductor. The circular mil area of a wire is a unit of measurement used to quantify the cross-sectional area of a round wire. It is defined as the area of a circle with a diameter of 1 mil, where 1 mil is equal to 1/1000th of an inch. The circular mil area is commonly used in electrical engineering to determine the ampacity and voltage drop of wires. The ampacity of a wire is the maximum amount of current that it can carry safely without overheating. The ampacity of a wire depends on its circular mil area, as well as the type of insulation and the ambient temperature. The larger the circular mil area, the higher the ampacity. Voltage drop is the decrease in voltage that occurs along a wire due to its resistance. The voltage drop depends on the circular mil area of the wire, as well as the length of the wire and the amount of current flowing through it. The larger the circular mil area, the lower the voltage drop. The circular mil area of a wire can be calculated using the following formula: circular mil area equals the square of the diameter of the wire in mils. For example, a wire with a diameter of 100 mils has a circular mil area of 10,000 circular mils. The National Electrical Code provides tables that list the circular mil area of different wire gauges. These tables can be used to determine the appropriate wire gauge for a given application. When selecting a wire gauge, it is important to consider both the ampacity and the voltage drop. The wire gauge should be large enough to carry the required current without overheating, and it should also be large enough to minimize voltage drop. The circular mil area of a wire is an important parameter to consider when selecting a wire gauge. The larger the circular mil area, the higher the ampacity and the lower the voltage drop. When dealing with voltage drop calculations, understanding the relationship between resistance, length, and material is crucial. These three factors are interconnected and significantly impact the overall voltage drop in an electrical circuit. Firstly, let's consider resistance. Resistance is the opposition to the flow of electric current in a conductor. It is measured in ohms and is directly proportional to the voltage drop. The higher the resistance, the greater the voltage drop for a given current. The resistance of a conductor depends on its material, length, and cross-sectional area. Secondly, the length of the conductor plays a vital role in voltage drop calculations. The longer the conductor, the greater the resistance and, consequently, the higher the voltage drop. This is because the electrons have to travel a longer distance through the conductor, encountering more obstacles along the way. Therefore, it is essential to minimize the length of the conductor to reduce voltage drop. Thirdly, the material of the conductor significantly affects its resistance. Different materials have different inherent resistances. Copper and aluminum are commonly used as conductors in electrical circuits. Copper has a lower resistance than aluminum, making it a better choice for minimizing voltage drop. However, aluminum is lighter and less expensive than copper, so it is often used in applications where weight and cost are important considerations. To calculate the voltage drop in a circuit, you can use the following formula: voltage drop equals current multiplied by resistance. The resistance can be calculated using the following formula: resistance equals resistivity multiplied by length divided by area. Resistivity is a property of the material, length is the length of the conductor, and area is the cross-sectional area of the conductor. By understanding the relationship between resistance, length, and material, you can make informed decisions about conductor selection and circuit design to minimize voltage drop and ensure the efficient operation of electrical equipment. When dealing with voltage drop calculations, you often need to determine the resistance of the wire. The resistance of a wire depends on its material, length, and cross-sectional area. The formula for calculating the resistance of a wire is as follows: resistance equals resistivity multiplied by length divided by area. Resistivity is a property of the material and is typically expressed in ohms per circular millifoot. Length is the length of the wire in feet, and area is the cross-sectional area of the wire in circular mils. The circular mil area is a unit of measurement used to quantify the cross-sectional area of a round wire. It is defined as the area of a circle with a diameter of 1 mil, where 1 mil is equal to 1/1000th of an inch. The National Electrical Code provides tables that list the circular mil area and resistance of different wire gauges. These tables can be used to determine the appropriate wire gauge for a given application. When calculating the resistance of a wire, it is important to consider the temperature of the wire. The resistance of a wire increases with temperature, so the voltage drop will be higher at higher temperatures. The National Electrical Code provides correction factors for temperature that can be used to adjust the resistance values in the tables. Understanding how to calculate the resistance of a wire is essential for performing accurate voltage drop calculations. By using the appropriate formula and the National Electrical Code tables, you can determine the resistance of the wire and select the appropriate wire gauge for a given application. The formula for calculating voltage drop is fundamental in electrical engineering and is expressed as voltage drop equals the current multiplied by the resistance. In this formula, voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Current is the amount of electrical charge flowing through the conductor, and resistance is the opposition to the flow of electric current. The voltage drop formula is based on Ohm's law, which states that the voltage across a conductor is equal to the current flowing through it multiplied by its resistance. Ohm's law is a fundamental principle in electrical engineering and is used to analyze and design electrical circuits. The voltage drop formula can be used to calculate the voltage drop in a variety of electrical circuits, including branch circuits, feeders, and transmission lines. It is important to minimize voltage drop in electrical circuits to ensure that equipment receives the proper voltage and operates safely and efficiently. Excessive voltage drop can cause equipment to malfunction, overheat, or not operate at all. To minimize voltage drop, it is important to use the appropriate wire size, minimize the length of the circuit, and use conductors with low resistance. The voltage drop formula is a powerful tool for analyzing and designing electrical circuits. By understanding and applying this formula, you can ensure that electrical equipment receives the proper voltage and operates safely and efficiently. To calculate the voltage drop effectively, it's essential to understand each component of the formula and how they interact. The voltage drop formula is voltage drop equals the current multiplied by the resistance. Let's break down each component. Firstly, voltage drop, measured in volts, represents the reduction in electrical potential along a conductor. This reduction is caused by the resistance of the conductor impeding the flow of current. Secondly, current, measured in amps, is the rate of flow of electrical charge through the conductor. It's the amount of electricity that's actually flowing through the wire. Thirdly, resistance, measured in ohms, is the opposition to the flow of current. It depends on the material, length, and cross-sectional area of the conductor. The formula highlights that the voltage drop is directly proportional to both the current and the resistance. This means that if you increase the current or the resistance, the voltage drop will also increase proportionally. For example, if you double the current while keeping the resistance constant, the voltage drop will also double. Similarly, if you double the resistance while keeping the current constant, the voltage drop will also double. Understanding this relationship is crucial for designing electrical circuits that minimize voltage drop and ensure proper operation of equipment. By carefully selecting wire sizes and materials, you can control the resistance of the conductors and minimize the voltage drop.